I would like to see all of you. And also by Zoom. Today we have some people on a sick leave, so I try to organize a Zoom for them, but I'm not sure that the quality would be good enough for them. Today we will talk about quite important thing. As soon as I will start the clicker in a proper way. Oh, okay. Okay, very good. So I'm ready to start. And today we talk about a quite important topic in processing of sequential data and in general in machine learning and deep learning. We'll talk about how can we use attention to improve our models, what the attention is, and I suppose we will have enough time to start talking about transformers and a bit how they changed the models in many areas, in particular in our area, in the processing of sequential data. We'll start far away, as usual, and talk a bit about how machine translation model works and what kind of machine translation models exist here, and okay, what's the problem in general. So we have two sentences, one sentence in source language and another one in target language. And so we want to have a translation from one language to another. And so basically we don't know why for sure. And what we know is X and want to construct a model, then produce Y in the end. And so the first generation was quite simple of this model. Like I look up in the dictionary for a particular word, find a translation, replace the word-based translation. And in the end, we have systems that kind of works, but the quality is for sure very poor because we don't have like strong enough model to take into account, for example, temporal dependencies. We just look at single word, and we can even like keep history about the gender, and it's important if you want, for example, a correct translation from Russian to whatever language we want. So this was not a very successful attempt, but at this time, in the 50s, we had no other options actually, just because, okay, machines was not very strong and so on. So there was another type of models that has like a general name, statistical machine translation. So basic idea is that what we want from machine translation is to learn the distribution of Y given X, where X is the word in the source language and Y is the word in the target language. And in this case, we want to find, if we have the distribution, we can find Y that maximizes this probability density, and this would be like a way to translate from X to Y. So the word, the sentence that has the maximum probability density in that. We can try to adopt some schemes. For example, we can try to use like Bayesian formula and try to do like in an inverse way. So we are not estimating the conditional Y given X, but instead X given I times the prior density for Y, Py, and then we can try to have these two separate models, translation model, this conditional density, and language model at like what are the probability of a sequence to occur in the language. This is a bit easier problem in a way, but still it's very hard because of like many problems which we want to solve here because of language is incredibly complex. And we have to give a good try to create like a reasonable, we can call it principled language model to deal with it. So in this case, you can say, okay, we have very strange and very complex results. And here you can see some problems here. So if we want to have some alignment, for example, we can try to introduce this additional variable, and you can see that it's another layer of complexity here, and it's kind of hard to think of this, hard to create some models. Also, okay, you can try other approaches, but again, we will have to deal with them in a very complex and tremendous way. And so the problem is not itself, when you consider it as an optimization problem, because we are searching over a discrete space. Even if we have a perfect model, we still have to search from almost incredible space without any reasonable representation which we can use instead in a continuous space. And so we can, for example, look at 3 of possible options and try to select the words one by one. So we start with decomposing this probability density into a number of terms, a sequence of terms. So starting with the generation of the first word given x, then the second word given the first word and x, and so on and on. But still, we are kind of looking for a heuristic which doesn't work perfectly all the time. So, for example, say something like this. But again, this is not like ultimate solution. And also we'll discuss an approach on this later, but again, even if this decomposition is exact, it's quite hard to deal with it and to provide like meaningful solution to the optimization problem. Also, you can see that this approach is kind of big. So it's like y1 as the first place, and the second word given the first and x and so on. So when we do something in greedy way, it's very high probability that we will miss some interesting solutions that really what we should look at. So another problem here. And this is not all the problems. I wouldn't mention all of them, but we can say that, okay, such system existed and they kind of work, but this can be quite hard to achieve good quality. In this way, you need a lot of tricks, a big teams of engineers to make it work. And we can say that we don't want to build the system one time, but we want to maintain the system. And it's another hard problem because of like the language changes, and we need to adapt to it. So we need to retrain this model, need to like invent new tricks, take into account some new things, or take into account, for example, that, okay, before we have long text in books and in letters. Right now we have shorter text in messages and SMS and so on. And in this way, we have to adapt, evolve, and this includes a lot of resources. Yeah, it's very hard to maintain like good language model after all. So, okay, we want something better, and this better way to do machine translation is based on neural networks. So again, we want to replace all this hard engineering with a single neural network. And like maybe the simplest idea here is to use 2 recurrent neural networks or 2 different neural networks of any types. One of these networks is an encoder, another one is a decoder. If we have an encoder, it produces an embedding after or this embedding is RNN blocks, some input words, embeddings for these words that we pass to RNN. So we have a word embedding in a state. Okay, apply recurrent block, have another in a state, another word, another RNN block with the same parameters, another in a state, and so on and on and on. And in the end, we have this embedding of the sequence. So we have this encoder block applied to produce an embedding. So we start to play with another neural network, a decoder. The decoder starts with some token, start of a sentence, and this in a state effect. Then it produces a signal state and logics for each token, so probabilities for each word to occur. And then we just take the word that maximizes these probabilities of each word in a dictionary. So we have the first word decoded, and we will go on with the second word. So we put as input our token decoded as the previous step, a signal state we had before, and apply another recurrent block here to produce a second word and another state, so we can continue decoding our sequence. And in the end, we have this specific token that designates that we reached the end of the sentence. And so we have now the whole sentence. For sure, we can apply some heuristics and say, okay, if we have two large sentences, then we just stop to filter out some garbage produced by a decoder, and so on. So this is the basic architecture introduced in 2013, I suppose. And we have like this encoding of a sequence, which we will try to explore more a little later. And so basically we have something we expected from statistical models. We have like language model and these conditional models. Also, as we deal with this single architecture, we can adopt it to solve various kinds of problems. So starting from summarization, so from a long text, using this sequence-to-sequence model, we can produce some shorter text summary. We can try to use it for dialogue systems, for parsing, even for generation of code if it replaces Russian or English language model. This model might by some programming language like C#. And so basically we can say that we learn these probability distributions of the data, and basically we again use this decomposition. So you produce the first word given X and continue on the way. This hidden state that kind of represents what we have here in the input sequence. So basically we have something we actually talked about like about a week ago. Also, to make this approach more successful, some engineering tricks also required. For example, it's a popular and working scheme for architectures to use Bing search. We say, okay, maybe the greedy way to generate tokens is not what we are looking for. Maybe some less greedy solutions would be better if we apply them in the right way. So what we are doing here? We start with the first step. We generate some probabilities of a token to occur for all words in our dictionary. And we are not looking for only one top token with a top probability, but for some tokens in this top list, for example, top 3 or top 4 or top 5. In this figure, we have top 2 tokens here. And so we continue to the second step. In the second step, we repeat the same procedure. We generate candidates. So if the first token is A, we try to find the most probable token during the second step. With the top probabilities given A is B. And the same approach we apply in the bottom, where from C, we try to generate the next token. In this case, it's E. So we now have a pairs of candidates, CA, CB up to CE, and again, like in the top AA and B, AC, and so on. Okay, we also can estimate the joint probability distribution for that. And we can try to find again top 3, for example, or top 2 candidates. In this case, candidates are no longer a single token, but a pair of tokens here. For example, we select A, B, and C that have the highest joint probabilities given our language model on neural network. And so we continue to the third step, when we again have some candidates and try to generate new sequences, select top candidates, and so on, until we reach the end of a sequence. In this case, we maintain some set of high probable candidates, they are more diverse, so we expect that them work better in practice and not as greedy as what we have before. So in this case, okay, we again have similar stepping criteria when we reach the end token or maximum length of the sequence. And also we say, okay, we have this m candidates after top m according to our procedure of selection of candidates. And we can, okay, to make it work, usually we compare not like the giant probabilities like this of y I single candidate given x, but just normalized probabilities normalized by the length of the sequence. If we apply this kind of procedure, we get this canonical implementation, canonical algorithm for binary search. And in this case, we have like this whole working system as simple as it is, as it was like about 8 years ago. And we can, if we can compare this approach to like the common approach, this ZER statistical learning translation, SLT performs significantly worse. Also, we don't need a complex system to do machine translation here. We just train the single end-to-end neural network, and it's kind of good thing because we don't need a lot of components there. Each separate component can fail in a way. Also, we can observe that this type of problems don't need significant human engineering. In this case, okay, this algorithm is as simple as this. So we have this initial architecture, like standard RNN, not that complex. This embedding layer to have embeddings of tokens, beam search to make it work better. And in the end, we have quite good performing neural network. Also, we can apply these techniques for like almost all language pairs. We don't need to invent new language model for new language because it sometimes can be quite complex and quite different from what we had before. And so in the end, we have this whole sequence-to-sequence model that kind of work for all. Also, a couple of words about how we evaluate these machine translation approaches. Any questions to previous part? No? Okay. So we say we have true sequence of words. Okay, the cat is on the map. Okay, it's on the right. And we have some candidates. And so we want to find how y and y hat resemble each other. We can start with a very simple metric, precision. So we are looking at share of words from this generated sequence y hat that appear in the initial sequence y. And so, for example, we generate all this the, and so on words. And in this case, we have like quite high precision, but it's kind of useless because okay, we see that unigram precision. So if you look at the single word is 1 because the word the appears here too. But it's not kind of good metric. It's not a good translation at all. We can replace any sentence with something like this and have high precision, but quite useless translation. So what we can try to do, we can, for example, limit this precision by taking into account how many words there are in the initial sequence. So we have only 2 words there. So our precision here is 2 divided by 6 because we have 6 words in total, and 2 is the number of words there in the initial sequence. Okay, but we can try to do more also and try to apply more heuristics to have more reliable and more natural metric to measure the machine translation quality. At first we say, okay, instead of unigram, we try to use bigrams. And so, for example, even for this a bit more sophisticated translation, the cat, we have this unigram precision again y, and bigram precision is quite low because we have only 1 bigram, the cat, that belongs to the initial sequence Y. Also, we can limit, using this trick, how many times we can count each unigram or bigram. So if we have this two there, one cat, so our unigram score, is not 2 divided by 6, but 3 divided by 6. And bigram score is 1 divided by 5, because we have only one bigram, so a sequence of 2 tokens, the cat, that occurs in the initial sequence. All other pairs like cat, cat, are not something we see in the initial sequence. So this is how we define block. So we say that we take some unigram, bigram. Typically, I suppose it's like we have, instead of bigram, we have 5 grams to compute, and also we limit precision by how many similar tokens or series of tokens occurs in the initial sequence to get blur. Good blur scores are about 0.7, and if you have significantly higher scores, typically it means that maybe we overfit into something. For n gram, we use n equals 4. So because it correlates best with the human judgment. And also we often look not only at precision, but also at recall. But right now we will see only through H-Boolean. And we can, for example, compare quality of different old models of machine translation with each other as the time progresses, like it was 2016, when narrow machine translation outperforms everything else, and we can see that it's what was like this from the beginning. So we need a couple of tricks and 1 year to make everything work better, but in the end we have better performance for narrow machine translation given blur score, and it's mine also best what we have. And also we observe engineering adoption, engineering qualification that it works good. So the first paper was published in 2014 and 2016. Google uses this sequence-to-sequence model instead of statistical machine translation in his Google Translate engine. And this is quite much easier to implement. So we have the epoch of deep learning in NLP data that started maybe in 2016, a bit later than in computer vision. Again, we have some problems to solve. They are not that important in this case, much less compared to statistical machine translation, because in SMT is quite hard to get good working system, as discussed before, but right now we have this out of vocabulary words. Again, some kind of mismatching between training and test data, but it's kind of easier to do because we can now train much faster without requirement to rebuild all the system from scratch. And also we have to maintain context from overload the text, which is also a problem. And it's a typical problem for recurrent neural networks because they kind of look specifically at this embedding in the end. And so they don't have large enough memory to maintain information about long texts. And also sometimes it works poor because we have don't enough parallel texts in some language pairs, which are served, for example, for summary English translation. Also, okay, this what like a prehistory. Let's start a story. And story is about transformers and about attention. And as we can look also at blue scores for transformers and compare them to recurrent neural networks and CNNs, which also works quite good here. And for transformer, we have this unnormalized blue score about 28 compared to 24 for RNNs, for what we had before in an approach, sequence-to-sequence approach I described before. This is for English and German translation. For English and French translation, we also have significant improvement of transformers compared to what we had for AGNs. So definitely transformers worth our attention, and this is what we will discuss a bit later. So the problem for this model, for RNNs, the main problem is this bottleneck in the middle. We have initial sequence encoder, all information stored in our embedding, and then the decoder. So the decoder looks only as this small part we extract, maintain, and so on. It's kind of crucial problems if texts are long, but even for small texts, we say that we can't remember anything, and probably we miss something from the beginning or in the middle that our neural network considers not very important. So this kind of problem. And so we will try to solve this bottleneck problem by some direct connection between inputs and outputs to make it work better and to drop this requirement on bottleneck. So try to replace it with something meaningful in there. We again look at sequence-to-sequence model, and I will start with explanation on the general technique here, and later some motivation and how and why it works. Okay, who of you knows about attention? Okay, thank you. Who can write all the, okay, there is a simple formula actually here. Yeah? So, but whatever. Okay, so what we say or how it works. We have some tokens in the initial sequence and some token as the output, for example, S1, like some hidden state. So we calculate attention scores in the beginning. And we say that we have some connection calculated on the base of the embedding we have now and how it connects to the embeddings what we have in our plan. So we have these attention scores. We normalize them to have the probability distribution instead of some numbers. So right now, each attention score is some number between 1 and 0, and they sum up to 1. So we have weights for these initial tokens. So we apply these weights to produce this final embedding we are looking for. So we now have this embedding instead of what we had before. And we can use this embedding to produce of this embedding and this initial token, the next token we have in our translation. Then we apply the similar procedure for the next token if we use a decoder. So we again calculate attention score between the current embedding and embeddings here. We normalize them to have weights instead of initial not normalized distribution. Then we have some embedding as a weighted sum, and we have another decoded sentence. So this is like an informal way, a picture to look at attention. And it's attention because we calculate how much we should put attention to a particular token here, how much we should involve with this particular token in calculations and output in the end. This is why it's called attention. Okay, so let's try to write down some exact formulas for our attention. Okay, as you know, after application of our recurrent neural network, in the end, we have encoding hidden states after each RNN block here. Yes, some H1 up to Htx, where Tx is the length of our initial sequence. Also, we have our decoder and also an RNN. So it also produces some hidden state from previous hidden state plus the token we decoded as a previous state. So it's St, for example, is also of the same dimension H. As time step, it, for example, St. So we start with calculation of the attention scores, the scalar product or correlation or what else we can call this guy, the scalar product of our hidden state and hidden state we have before in our initial sequence. So we calculate this attention scores here, yeah, in again it of length tx, but tx is less of constant. Okay, it's not a probability distribution. So we apply softmax as similar to classification to get probabilities instead of this initial scores or attention scores. So right now we have alpha t, and each alpha t is something between 0 and 1, and all alpha t's sum up to 1. So this is a vector of weights. And now we can get our weighted sum of hidden states given the weights produced by attention. And so we have this attention part of the embedding and initial part of the embedding. And now we can produce this guy, this vector concatenation of AT and SC by a sequence-to-sequence model to have the output. So basically, it's all about this basic attention for recurrent neural networks. Okay, any questions? Yeah.
Gradient with respect to the states, because we reduce them a lot of times in the model, and we just keep a zero gradient with respect to the or calculate it every time.
I think we use some time, some widths here, and also okay, we can directly propagate all these things like this quite simple formulas here. And I think we just limit how much terms we think. And also typically these models are quite computationally heavy. So we have to spend a lot of time to train typical attention models because, and again it's a very big problem for attention models actually. Because we need a lot of time to calculate the output if the length is also high. Just have to multiply all the stuff each time, and you can estimate like this. Would be not an easier way to get O of gx times gy because of what we generate, and also in each particular case we calculate. Oh gosh. Yeah. So it's proportional to the length of initial of output sequence and the hidden state dimension, which is not very good in my opinion. Okay, not very easy to do in my opinion, but for transformer it's even worse. So basic attention is quite easy to calculate and easy to backpropagate compared to transformers, which we look a bit later today. Any other questions? So everyone understands how it works and how, for example, we can backpropagate through it and calculate also the derivatives. Yeah. Okay. Hope so. Okay. Also, please. Okay, so we have our attention now, and we can try to see how it works. It works very good, and also it has something interesting properties that solves not only the bottleneck problem, but also other problems we mentioned when we were talking about RNNs. We talked about that we have vanishing gradients, exploding gradients, and so on. As we no longer have the sequential proceeding of gradients, we kind of solve the problem with exploding gradients and also with vanishing gradients because we have this all-tone connection. We have connection of all tokens in an encoder and in the decoder. So we have this non-vanishing gradients, and we no longer should care too much about this. Also, we can try to have some interpretability of this model. We can try to align the token from initial sequence as possible Chinese and in English as our target. and we can call on, for example, attention score between the source and the target language and say, okay, maybe this is the most connected path, and we as I enter the first sequence, enter the second sequence, and but also we have some things to connect to. For example, maybe this guy means no, and this guy means strong. At least we can suppose something like this. It's not kind of ultimate measure on the importance of a connection, and there are some problems with this interpretability, but at least it is something better than we had before. And also, as we look at the whole sequence, we have higher hopes on how we should connect, and that true importance will be brought to attention scores, that what we will have, for example, when taking the derivatives with respect to the embeddings of the initial tokens, the impact on the output. So we have architecture that's kind of similar to recurrent neural network. We can use any recurrent neural network block here, but it's greater in terms of quality, interpretability, and like many other natural properties. Also note that this kind of general idea thinking in machine learning, we can try to apply the similar idea in any other NLP problems in sequential data processing. So we can try to look not at tokens in a sequence, but also at event sequences, or like general multivariate time series and so on. And again, we will have attention between the input and the output, and this is beneficial in many terms because we don't forget about our past history, improve, and so on. Also, we can try to apply something like this with, for example, graph neural networks. In this case, we can also introduce some kind of attention between, like, for example, nodes in initial graph and in other graph, and so on. And if we look at this problem from a more general point of view, we have this key value interpretation of the attention. So we have some query to a database for a sequence-to-sequence model. It is a hidden state of the decoder. Some keys in the database, some like what we have in our database here, hidden state of the decoder for a sequence-to-sequence model array, and some values we want to extract to get. And then this is also hidden state of the encoder for our sequence-to-sequence model. Then we calculate some correspondence between query and key. So how connected this query to a particular key. Then we can get the weights on the basis of this attention scores of these correspondences and extract some information like as the weighted sum of this attention scores, alpha, like of this normalized correspondences, and our hidden states are values of the database. So we can look at attention at a way to get information from the database. Like you can apply it in any framework like this. And also you can see that actually we pay not much attention to a particular order in the sequence. So we just calculate these formulas here, and you can see that we have no dependence on the number of the token in a sequence. We will talk a bit on how we deal with it, because, okay, generally we are talking about sequential data, so maybe we should include something about sequential nature of the data into our model to make it better. But overall, the idea is like this. And it's quite similar to this key value interpretation if you look at it in a more broader way on how attention should work in many other areas. So we talked about transformers, or excuse me, about attention, and now let's talk a bit about transformer model and how it is different from the basic attention. Spoiler, the idea is quite simple. We want to have more layers. So basically we have for usual attention, sorry, let's go back. For usual attention, we basically have one layer of attention. We have this scalar products, we produce the base, and so voila, we have in the end this embedding. We want to do this. But maybe if we somehow manage to have more layers of attention, we'll have a better model. Okay, these things that all practitioners do. Let's try to make something a couple of times instead of one time and hope that it will be better. So let's see. Again, this key value interpretation, maybe to write it a bit more formally. But okay, you already saw all these formulas. Again, we have this attention scores, scalar products of queries and keys. In this case, queries corresponds to this S. We have this softmax, we have probabilities, and then we have this weights. Okay. Now so formula is like this for this correspondences. If we rewrite it in the form of correspondences of matrix form, we have like this. So we have this attention scores normalized, and then we have this values. In this case, we are looking not at a single part of the single query, but we can imagine that we have a lot of queries, and for each query we calculate separate attention scores, and in the end we have this great attention matrix. Sorry, attention. Is it matrix or vector? Yeah. Why? Okay. So to make it transformer, we applied one trick. We say that right now we're looking at many queries at the same moment, so we can apply matrix formulas and calculate everything in a fast way. And also we have this new scaled formula to make it work better, some heuristic, just divided by how many keys do we have. So we normalize like this. Somehow it works better. Okay. Also, we say that we have this attention and we have this RNN part. So we need RNN part. Maybe we can just drop it and keep only the part that's related to attention. And we, instead of attention, use self-attention to find these connections between the tokens in our initial sequence. So we calculate attention between our sequence and the same our input sequence to have this new embeddings as a weighted sum of all the embeddings. And we can repeat this operation for a couple of times and have like this self-attention that leads us to the transformers. Also, a couple of additional things to make it work better. Additional parts is multi-head attention. We can use not a single attention head, but a couple of attentions here. And also we need a feed-forward layer to make it work better. So we have some inputs. We have input embedding similar to RNN. We have, for each token, we have some embedding. For each dot, we have some embedding. Then we add this thing. We talk about a bit later positional coding. So that to this embedding a constant vector, constant with respect to some position in a vector. And then we proceed, we input these embeddings to our attention, to our multi-head attention, to have the output of this multi-head attention, some normalization and skip connections, feed-forward neural networks, and so on. And we are ready to repeat this operation n times. So what's going on inside this third attention block in more details? We see we have the queries, keys, and values. Queries and keys and values are actual our embeddings here for our initial reference. And so we calculate this attention for them, normalized by decay. So we like kind of try to avoid complex things here related to large values. Also, we get some maybe optional mask scaling, softmax, and also some modifications. So this is what we have in this attention subblock. So this is our very modified attention. And also we can have note that we can have this additional trick to make it work better. So basically we have this embeddings. We multiply them. I'm sorry, this is here should be WK and WV. And we have now queries, keys, and values instead of initial embeddings. And also we can have this weight matrix different for different heads of our attention. Is it clear? Yep, or not? So this is what we have in our block for multi-head attention. So again, we have these indexes for each head of our attention with total number of heads h, and as index for particular head is I. So now we are able to calculate these attention heads. Now we can try to add another block related to the modification of our neural network. And in this case, we apply ReLU activation function for our outputs with some weight metrics in our feedforward model. So we have a linear transformation of our values, ReLU function, a nonlinearity, another linear transformation, and embeddings in the end. So this is what we have for one attention block. Input of this block is some kind of queries, keys, and values, or just a single matrix that represents queries, keys, and values. We apply multi-head attention to get modified embeddings with attention applied to the same elements to have output here. And we apply also some linear transformation, so it makes sense to apply more layers like this. And as the output of our attention block, we also have some matrices of keys, queries, and values, or a single matrix that again represents all these three types of information we need here. And we repeat this block for 6 times to get the output of our transformer architecture. So we have the output of our transformer as an output of this deep neural network. Okay, maybe a couple of words about normalization and what we are doing here. We just say that we have this skip connection. So we have this x here, x preceded by multi-head attention. We add the same x here. And also we have this normalization like this. Okay. Some last part in the very beginning here. What kind of positional encoding is possible? Okay, the first option is to just have something like this. So let's say we have this position number. We have some parameter d and I, and we calculate sine and cosines here. For even number, we have sine. For uneven number, we have cosine here. And this is our positional encoding. And we have some embedding of words here. We add to positional encoding. And so we have this x. Also, I'm sorry, we have this I parameters that reflect that we can type more embedding or more positional embeddings here. Okay. Okay, for the decoder, we apply something like this. We have something, for example, we want to decode starting token, we add positional point, and then we have this self-attention here, and also not self-attention, but usual attention between inputs, that's the output of our encoder, and our decoder, which we want to use to decode something. In the end, we have some embeddings after application of, as far as I can remember, also 6 layers transformers here. And these embeddings can be, after a linear layer, are used to decode a sequence because, again, we have this vector of probabilities of particular tokens. Also, we can say that in the decoder, we don't have this full attention that we do. We can try to start with decoding of one token and proceed with the next token because we have only one. So we say, okay, we have this embedding of the starting token, and we have our self-attention here and encoding of our initial sequence. So we can calculate the attention and produce the token here. Also, we for sure can try to visualize all these things. And we can, for example, try to compare different words in input and output. And for example, we can have, I suppose it's as the same sentence, but we can say that for making, we have self-attention of making and more difficult. But for each, we say that it's connected to law. So we definitely uncover what it means. It means that this is the law we have here. Okay, this was about how we apply these models. We can for sure try to use backpropagation, but maybe more interesting way and more successful way to train this kind of embeddings and this kind of models, because of the self-attention nature, is mask language model. The idea is that we should replace some parts of our sentence with some nonsense, and then try to recover the initial sequence x1, x2, x3, x4. We replace the second token by some mask, and we try to recover it back. So make it as close to x2 as possible to get the correct prediction in the end. Again, we have this transformer in the middle to produce this type of outputs. And also we can say that it's kind of successful kind of after regression training of the model. For GPT, we do something similar, but we predict not something in the middle, but predict next token. But again, we apply this decoder and transformer and see that is how it works. For different problems, different types of this model training is better, and one should consult literature on what kind of model you should use for a particular problem. Also, as you can see, this kind of self-supervised models, you just don't need like elaborate examples to make it work. We just generate these training pairs from scratch. We have a sequence, we mask some part of the sequence, and we try to recover it. So we don't need any supervision. We just rely on how we drop or mask tokens in the initial sequence. Again, for GPT, we drop last token and try to predict it. And again, we don't need any supervision. We are supervision itself. Okay, so we are doing self-supervision. As you know, maybe most of you, this kind of models are very powerful and very large. Okay, there are types of GPTs, like I suppose a GPT article, and you can see that we can range number of transformers, number of transformer layers, number of the dimensionality of the model in a large scale. So we start with small one with only 12 layers and go on with GPT-3 with 96 layers and about 200 billions of parameters, a lot of heads and so on, a lot of also not the batch type structure. 3 billions here. Okay, but as we define this model, train them for a long time, we see that in the output we have kind of good accuracy here. This very large confidence. So what experiment is here? We show generated sequences to humans and see how accurate are they at distinguishing artificial sequences produced by different variants of GPT and actual sequence. And for some like basic baseline generative model to generate some sequences, we see that accuracy is quite high, 86%. So humans are pretty good at distinguishing these artificial sequences and initial one. But if we try to increase the quality and the quantity of parameters in our GPT models, as we proceed, we see that our quality improves. So human no longer can distinguish generated and actual sequences. For example, if let's say for something in between with 2.7 billion parameters, we have an accuracy of 62%. And if we further increase the number of parameters in the model, we have something like 52%, which means like humans can distinguish artificial sequences and actual sequences when we look at it. So we can state that as a way to train generative models, transformers and this auto-regression approach for self-supervised training of them are quite efficient, and also it matters how many parameters we use. We say that, okay, if we are talking about big data for training, we need big models, and as our model size increases more and more, we have significantly better models in the end. So we don't observe any overfitting here. As we have more parameters, we have better models. This kind of general phenomenon in deep learning, and we can say that we observe it here in transformers. For RNNs, I suppose we have typically some strange effects connected with gradient vanishing and gradient exploding, and also with training for very long sequences. But for transformers, if you are doing everything right, we say that we no longer suffer from overfitting and these strange numerical effects. We have, as we have more parameters and more data, we have better models, and we can continue on and on as we have money to train these models and electricity. And this is what people are doing. They are trying to increase the number of parameters and see what's going on. So there are different types of transformers, basically. And we see that, okay, we have this big GPT, 175 billion of parameters, much better, much bigger than other models, and much better. And also maybe it's better to put this in logarithmic scale to have like reasonable comparison. But okay, and also maybe I should update this slide, these models from 2022, because we have bigger models here and so on. Okay, so we tried to familiarize yourself with attention mechanism. In its basic implementation, you can apply it to recurrent neural networks, and it works quite fine. And you can improve machine translation models even with this simple attention, because you'll be able to look at long histories of data. But if you want better models, kind of simpler but more efficient, we can use this transformer models that is based on stacking multiple layers of attention to get better representation, to get better connections between different types of embeddings to produce the good model in the end. And as we like implemented and invented this kind of architecture, we can try to make it better by putting more and more data in it and putting more and more layers in it. And so we can say that we ended up with quite large models that are possible to train for a single human or even a single laboratory, I suppose, but that can work quite efficiently. During the next lectures, we'll try to look at transformers from different point of view. For example, we'll try to see what we can do if we want to minimize the size of transformer. So how can we apply transformers more efficiently? Also, we'll try to look at attention in more details and see how we can interpret this attention. Is it really interpretable or not? So this is what we're going to do next lectures. And for today, that's all for a lecture. And in 10 minutes, Artem will give you a seminar. Artem is my PhD student and also a Sberbank employee. He's quite good. And the seminar is quite good. I take a look at it yesterday. So, a break.